Experts in space astronomy and physics continue to examine and be very interested in black holes, one of the universe's most puzzling and peculiar occurrences. Black holes, which are distinguished by their enormous gravitational force and complete lack of light emission, constitute an unbreakable boundary. The established principles of physical science are no longer relevant. Black holes were first postulated by Albert Einstein in 1916 as a direct consequence of the general relativity theory, but they remained completely theoretical until the 20th century, when advances in technology made it possible to detect them indirectly. An important turning point was reached in the 1960s when astronomers researching the Cygnus constellation unintentionally found a strange celestial object, a brilliant blue star that was releasing enormous quantities of X-rays. Until it was discovered to be in a gravitational interaction with a gigantic black hole, this star circling an unseen companion defied accepted explanation. Cygnus X1. A new era of research into these cosmic mysteries began with the finding of Cygnus X1, which offered convincing proof of the existence of black holes. Cygnus X1, which is almost 6,000 light-years away from Earth, has amazing features. Because of its extreme density and powerful gravitational pull, not even light can escape its hold. This distinguishing characteristic gave it the moniker black hole, which perfectly captures the spirit of these enigmatic phenomena. Numerous black holes have been discovered across the cosmos by later study, with estimates indicating that the Milky Way alone may contain over 100 million black holes. Astronomers have discovered a number of possibilities inside our galaxy, ranging from supermassive black holes at galactic cores to stellar mass black holes generated from the debris of enormous stars, despite their elusive nature, which makes direct detection difficult. Beyond their immediate neighborhood, black holes' gravitational pull shapes the development of cosmic structures and affects the destiny of matter in their surroundings. The extreme gravitational pull of a black hole determines the destiny of objects that approach it too closely. They will always be pulled toward the direction of the event horizon, the last barrier, where they will be devoured by the black hole's core singularity after being exposed to strong tidal forces. The ultimate expression of a black hole's gravitational power is this catastrophic collision, which is called spaghettification. The gravitational gradient along an object's length is so strong as it gets closer to the event horizon that it is stretched and twisted into thin, spaghetti-like strands. The item disintegrates into a stream of matter that eventually merges with the singularity when the tremendous pressures overwhelm the internal ties holding it together. Black holes are still mysterious despite their appeal as test sites for the boundaries of physical theory. The need to comprehend the basic nature of spacetime and gravity itself is what motivates the ongoing effort to uncover their mysteries. Even though there is a great distance between us and the closest black hole, roughly 1,500 light-years, questions and worries about their possible impact still exist. Black holes are silent sentinels in the vastness of the universe, urging humanity to delve deeper into the unknown and expand our understanding. Researchers made history in 2021 when they successfully captured the first unclouded photograph of a black hole, namely M87, which is situated in the heart of the Messier 87 galaxy. This outstanding accomplishment gave important new information on the characteristics of black holes. The conventional view of black holes as separate, pure entities of nothingness is challenged by the visual evidence, which showed that they contain intricate structures. 3 separate levels inside a black hole were discovered by scientists using painstaking research and picture stitching. The event horizon, a crucial barrier that denotes the point of no return, is located at the outermost layer. Gravitational forces become insurmountable once crossed, guaranteeing that the items will inevitably collapse inward. The second layer, known as the photon sphere, is where light circles the black hole perpetually. Photons that enter this region are defeated by the strong gravitational attraction and are forever imprisoned inside the cosmic embrace of the black hole. The singularity, the third and last layer where the rules of physics completely collapse, is located in the center of the black hole. The accepted laws governing the cosmos stop working, forcing scientists into a world of speculative guesswork and tremendous unpredictability. Understanding black holes is severely hampered by theoretical complexity and intrinsic variability. Despite having a similar three-layer structure, each black hole has unique characteristics and actions that make them difficult to classify. As a result, conventional scientific techniques are inadequate for understanding these cosmic giants, demanding the development of novel strategies to solve their secrets. Black hole research is still mostly conducted via indirect observation. Since their gravitational forces provide such formidable obstacles to direct examination, despite the fact that efforts to send probes into black holes would unavoidably be destroyed and reduced to obscurity by the unrelenting forces at work, scientists continue to work toward understanding these cosmic giants. Numerous hypotheses, ranging from cosmic dynamics to stellar collapse, provide intriguing insights into their causes and actions. Especially NASA's investigation of M87's cosmic core produced strong evidence of a super-large black hole, demonstrating the impact of gravity on enormous cosmic scales. Despite these obstacles, humanity's innate curiosity and need for understanding fuel the never-ending quest for knowledge. Even while the mystery of black holes may be beyond easy explanation, a dedication to scientific research promises to shed light on the universe's darkest recesses and unveil its most profound mysteries. Roy Kerr's seminal 1963 study offered a paradigm that changed how people thought about black holes. He proposed a novel explanation for revolving black holes, often known as Kerr black holes, which never cease spinning. The aerosphere, an area encircling the black hole where various forces balance gravity collapse and prevent everything from plunging straight into, was a fundamental idea in Kerr's model. This new realm showed intriguing characteristics that deviated from accepted physics and hinted to the enormous mysteries that lie inside black holes. However, Kerr's theory's prediction of an Einstein-Rosen bridge was perhaps its most exciting consequence. Known colloquially as a wormhole, this hypothesized structure offers a channel between far-flung parts of the cosmos or possibly to alternative worlds, representing a possible space-time gateway. Interaction between general relativity and the explanation of reality. Einstein's general relativity theory fundamentally altered how we see the world. Within this paradigm, existence is stitched into a single, four-dimensional fabric called spacetime. Massive objects distort this fabric, producing gravitational fields that influence the motion of nearby matter. Wormholes effectively serve as shortcuts through this cosmic fabric, allowing for quick travel across enormous cosmic distances and linking disparate locations in spacetime. The stability and usefulness of wormholes, despite their attractiveness, are still hotly debated topics among theoretical physicists. Wormholes provide alluring prospects for time travel and interplanetary travel, but these idealistic aspirations are tempered by substantial challenges and limitations. Wormholes' inherent instability combined with the significant obstacles presented by radiation and quantum forces cast doubt on its feasibility as a mode of conveyance. Furthermore, even if stable wormholes existed, they may not enable faster-than-light travel, which is a mainstay of many science fiction stories, since Einstein's theory of general relativity places basic restrictions on the speed of passage across spacetime. The allure of wormholes remains a source of scientific interest and research despite these obstacles. The concept of the wormhole, as termed by its first researcher, represents the alluring promise of cosmic gateways and other worlds that invite people to reflect on the secrets of the cosmos and the unthinkable possibilities that await them. The search for a theory of everything has been sparked by the need for a single theory that unites the apparently disparate fields of quantum mechanics and gravity. A thorough framework that can include all of the universe's basic forces and particles. Leading this effort is the renowned theoretical physicist Myoku, whose innovative contributions have advanced the field of superstring theory research. The universe's symphony and superstring theory. Superstring theory is a significant divergence from traditional theories. It makes the assumption that basic particles are minuscule vibrating strings rather than point-like things. According to this paradigm, the universe resembles a vast orchestra, with each particle representing a distinct harmonic resonance of these fundamental strings. These strings, like the strings of musical instruments, vibrate at specific frequencies, giving rise to the various particles and forces observed in nature. The ability of superstring theory to explain mysterious phenomena related to black holes, wormholes, and other unusual solutions to Einstein's equations of gravity is among its most remarkable applications. Topological anomalies and gravitational singularities are created by the dynamic motion of strings as they move across spacetime. However, superstring theory's fundamental complexity is hidden by its beauty. In addition to the well-known 3 spatial dimensions and 1 temporal dimension, it demands the presence of more dimensions. Human intuition is seriously challenged by these hidden qualities that are invisible to the naked eye. However, applied models provide insights into the elusive nature of these higher dimensional worlds, such as the comparison of fish living in a 2-dimensional lake. Although their effect is woven into the very fabric of reality, these additional dimensions are undetectable at ordinary sizes due to their compactification, which is similar to folding a rolled-up sheet of paper. Although the exact nature of these hidden dimensions is yet unknown, their existence theoretically provides a potential explanation for the universe's intricate patterns and abnormalities. The theory's limits and mathematical beauty. Additionally, the mathematical foundations of superstring theory have spurred a resurgence in mathematical physics, exposing deep links between mathematical dynamic patterns and physical occurrences. Actually, the pursuit of a universal theory has sparked a more thorough examination of the relationship between mathematics and the natural sciences. Superstring theory is still an unproven paradigm that desperately needs experimental confirmation, despite its theoretical beauty and scientific promise. Superstring theory is now limited to mathematical conjecture due to the elusive nature of additional dimensions, which poses a significant barrier to proof. However, the ambitious idea of superstring theory still fascinates scholars and enthusiasts, inviting people to go out on an intellectual adventure. We face the great secrets of the world as we delve further into the fields of theoretical physics led by the dazzling beacon of superstring theory, which stands at the cusp of a new age of comprehension and enlightenment. An emerging horizon and quantum black holes. For a long time, physicists have been baffled by the problem of discovering the secrets of quantum black holes, which poses a significant obstacle to our comprehension of the basic nature of the world. Despite several attempts, a conclusive answer has not been found. This led Princeton's Institute for Advanced Studies Edward Witten to characterize superstring theory as physics that unintentionally entered the 20th century, but fresh developments have revitalized the quest to comprehend quantum black holes. A number of physicists have independently reported a major discovery that suggests string theory may provide a complete solution to the issue, albeit in the more limited context of 2 dimensions as opposed to the complete 10-dimensional framework proposed by conventional superstring theory. This is a positive development. The intricacies of the problem continue to pose significant challenges in the pursuit of a comprehensive settlement. The pursuit of a cohesive theory pushes us to go into the most profound reaches of cosmic existence, where the lines between theory and reality blur and the universe's mysteries lie waiting to be revealed. The study of black holes has significant ramifications for how we perceive the world, appending our preconceptions and prompting inquiries about the essence of existence itself. The interaction of black holes with other astronomical phenomena, such as neutron stars and gamma-ray bursts, reveals the complex mechanisms at play in the cosmos.